2.3 yesterday, and we had just started talking about transformations. So let's see, we had worked through what happens if you move your graph vertically up or down. How does that change your graph? And of course, we looked at the changes that can happen with domain and range depending on what kind of function you have. Okay, so let's go ahead and continue where we left off at. So let's see. Okay, so we had finished talking about this last example here by moving our graph vertically downwards. So now we want to look at horizontal translation. So horizontal translation, of course, will move your graph left or right. Now, in this case, it's actually going to be interesting. Unlike what we did yesterday when we were moving our graph up and down, the basic idea was if the number you are adding is going to be positive, the positive tells you the graph is going to move up. If you are going to be subtracting, which means if you have a negative number, that means your graph moves down. But with horizontal translation, it's actually the opposite, because by default, we always define our function as y equals f times x minus h. So since we have a minus sign here, what that actually means is the number you are adding, this h value, is actually positive. So if h is positive, you are going to have a minus sign there, and that tells us we are going to be moving h units to the right when h is positive. If h is negative, that means your graph is going to be moving h units to the left. But what's going to happen is in here, in your basic equation where you have y equals f of x minus, but if h itself is a negative number, those two negatives are actually going to end up becoming positive. So what that means, if you look at example 3 over here, I have x minus 3. So the minus 3 actually tells me 3 itself is a positive number, and that means my graph will be moving 3 units to the right. So you have to actually go with the opposite sign than what's given to you in the function. So as I was saying, since you have x minus 3 here, that tells you 3 itself is a positive number, and that's why we're going to be moving to the right. If you look at our next example here, you can see I have x plus 9 inside the square root. So this technically means you have x minus negative 9. So since the 9 itself is negative, that means we will be moving 9 units to the left. So with horizontal translation, you actually have to go in the opposite direction. So if you see a minus 3, that means your graph is moving to the right. And if you see a plus, you're moving to the left. And remember, for horizontal translation, these numbers have to be added or subtracted from the x variable, not from the function itself. So what I mean is, if you go back and look at the original equation, this x minus h right over here on that first form we had looked at, this here is telling us you have a horizontal movement left or right. This k, which is basically at the end of your function, is moving your graph up and right. Up and down. So, it's kind of interesting when I talk about it in that sense, because, when we had this x plus 3 here, technically our graph moved up and our graph also moved left. So if you have this from yesterday in your notes, you can kind of look at it, or you can look at the notes I posted. But in this case, technically our graph moved, because, remember, it moved 3 units up, but then being a straight line, it also ended up moving 3 units left. So you actually had both movements happening here, though, we didn't do that intentionally. And so, some functions, it's going to be a little bit different, but this one is specifically going to be just moving our graph, 3 units to the right. So let's go ahead and take a look at what this would actually end up looking like. So let's do the first one here as our x square table. And we'll do the second one here for our x minus 3 squared table. So let's go ahead and see again, your x square, you can again use -2, -1, 0, 1, and 2, and we saw this yesterday. So again, you can do 4, 1, 0, 1, 4. And when you graph this, of course, your graph is going to be your basic parabola. Okay, and so this is our y equals x squared function. Now, like I said, with the x minus 3 squared function, the second one, since we have that x minus 3, that's telling us our graph is moving 3 units to the right. So hopefully once we're done with our table and we graph it, you will be able to see that. So in this case, what I'm actually going to do is I'm going to take all of my original x values that I have here in the first table, -2, -1, 0, 1, and 2. And to each of these, I'm actually going to add 3 to them. And you will kind of see why I'm doing that. So if I take my -2 and I add 3 to it, I will of course get +1. So I'm going to use that as my x value. I'll take my -1, same thing, add 3 to it, which will of course give us 2. 0 plus 3 will give us 3. Of course, 1 plus 3 would be 4, and 2 plus 3 would be 5. Now, if you use these x values, the 1, 2, 3, 4, 5, and put it into this function here now, x minus 3 squared, hopefully we will see the same y values as 4, 1, 0, 1, and 4, but let's verify that. So if I use 1 as my x value here, I will get 1 minus 3, the whole quantity squared. So 1 minus 3 will be -2. -2 squared will be 4. So we get a 4 here. Again, check the same thing with the other. So 2 minus 3 squared would be -1. -1 squared would be +1. 3 minus 3 will, of course, give us 0. 0 squared, of course, will be 0. 4 minus 3 will be 1. 1 squared, of course, is 1. And as you can see, 5 minus 2 will also be 2, and 2 squared will give us 4. So we knew our graph was moving 3 units to the right, so that's why we just took our x values and added 3 to it, and you got your new values for the second function. And now when we graph this, you will have 1, +4, 2 and 1, 3 and 0, 4 and 1, and 5 and 4. And when we graph this, this will be our function that has now moved 3 units to the right. Okay? And I actually wanted to show you this just to give you a little bit of a visual. I'm going to show you how to do this on our Desmos calculator here. So we've got our x squared function. Now if we do the x minus 3 squared, you can again see how that graph moves 3 units to the right. So in the red, you have the original, and you can see each point on your function over here. Let me see if I can. Yeah, so if you just look at these points over here, so this one here is at, right there we go. You've got 1 and 1 over here, and this same point has now moved 3 units to the right, and of course you should be at 4 and 1 over here. So each of these points, you can try and do that on your function, and you will notice all the points on your graph move 3 units to the right. So just like we did yesterday, I'd like you to tell me for the original function what the domain and range are, and how have they changed for the second function where we moved it to the right-hand side. So what can you say about the domain and range for the x squared function, the original function? Okay, domain would be going from negative infinity to positive infinity. Very good, Meredith. Yeah, because again, you're heading in both directions. What about the range for the original function? Okay, Jack, you are saying including 0 to infinity. Yeah, because again, your graph is going upwards, right? The arms are going up. So that tells you you're going from 0 to infinity. There is no graph on the negative side of our y-axis. And obviously, we are including 0 because we do have a point on our 0, 0. Now, by moving this graph 3 units to the right, did that change our domain and range? No, because as you can still see in the graph, our arms are still going to go left and right, which means they're still going to go towards positive and negative infinity on the x-axis. And even though our graph moved to the right, it is still on the x-axis, right? Your arms are still going up. So that part of our graph hasn't changed. So this is, again, one of those examples where by making this transformation happen, it did not affect your domain and range, okay? Alrighty, very good, guys. So this was seeing what happens when your graph moves to the right. Now let's take a look at the second example where our graph will be moving to the left. And as I was explaining it to you before, since you have x plus 9 here, that technically means we have x minus negative 9, and it's these two negatives that makes this a positive. And since this is a negative 9, that's why we know our graph will be moving to the left. So for the first one, we can go ahead and create this table for just the square root of x function. And then for the second one, we can create the table for the x plus 9 square root of x plus 9 function. So remember again, as we saw in section 2.2, that since this is a square root function, you are going to have restrictions because remember again, square roots cannot have negatives inside of them. So when you select numbers for this, pick numbers that would be perfect squares that would help you, get nice and clean answers. Square roots can have 0 in them, so we will start with 0. We can do square root of 1. And then like you saw yesterday, we can do square root of 4, square root of 9, square root of 16. Though we won't be able to graph that 16 over there. So when we take square root of 0, we get 0. Square root of 1 is 1. Square root of 4, of course, is 2. Square root of 9 is 3. And square root of 16 is 4. Okay? So we have all of these x values over here now. So can you tell me what kind of x values we can use for this second function over here for the square root of x plus 9? And I'm just going to go ahead and graph our function here. So this is your y equals square root of x function. So what kind of x values do you think we should use for square root of x plus 9? Because now remember how we did in the previous example, our function will be moving 9 units to the left. So what that means is basically if you take all the x values we have in the original function and subtract 9 from each one of these. So let's see, if I did 0 minus 9, of course. Yeah, basically that's the idea, Meredith. Yeah, numbers so that when you add them to this positive 9, it will still give you perfect squares. Yeah, very nice. So if you actually just did with these original x values, you subtracted 9, you should get all perfect squares when we do the calculation. So 0 minus 9 will of course give us negative 9. 1 minus 9 will give you negative 8. 4 minus 9 would of course be negative 5. 9 minus 9 would give us 0. And probably, I'm not sure if we'll be able to graph this or not, but we'll go ahead and check for it. 16 minus 9 will, of course, end up giving you 7. Sorry. Yeah, 7 as your answer. So what kind of y values are you looking at for this square root of x plus 9 function then? Just think about this. If you did, now that we have our x values, yeah, very good, Meredith. We have our x values, you just put that in your function over here. So square root of negative 9 plus 9 would be square root of 0, which is, of course, 0. If you did, very good, Lori, square root of negative 8 plus 9, that would be square root of 1, which would, of course, be 1. Square root of negative 5 plus 9 would, of course, give you 4. Square root of 4 is 2. Because, you know, we subtracted 9 over here when we came up with the x values, and now we're basically adding 9 back into it. So you're basically nullifying those values. So you should get square root of 0, 1, 4, 9, and 16. And then the answers accordingly. Same thing here, 0 plus 9 would give you square root of 9, which is 3. And again, square root of 7 plus 9 would end up giving you square root of 16, which would give you the answer 4. So you should be coming up with the same y values as we did for the first table. Now let's go ahead and graph this and see what we end up with. So we're at negative 9, 0, which would be here. Negative 8, 1. Negative 5, 2. Okay, and then 0 was at 3, and 7 was at 4. Okay, so this is kind of what this shape of our graph would end up looking like. And this is for y equals square root of x plus 9. And again, you can clearly see that the original function y equals square root of x was starting at the origin 0, 0. And by adding that 9 to our x variable, you can see our graph has moved 3 units to the left. You know, the other thing you could have done to try and see what x values you can use is something we had talked about previously. So since you have square root of x plus 9, we know the inside value cannot be a negative number, right? It can be 0 or it can be positive, which means the value of x plus 9 has to be greater than or equal to 0 because it cannot be negative. If you just simply solve this, you know, move that 9 to the other side, you would end up getting x has to be greater than or equal to negative 9. So again, that gives you a starting point because that tells you you cannot use numbers smaller than negative 9. So you can use negative 9 or anything bigger than that. And of course, you can see that's what we have in our table over here. So that's another way you could have come up with what values of x are you allowed to use inside the second function over here. So that's another way to look at it. All right, now if you will, please go ahead and tell me what the domain and range for these functions should be. So let's start with the original, y equals square root of x, and then we'll do for y equals square root of x plus 9. So let's do the main function first, the base function y equals square root of x. What do you think its domain and range is going to be? Okay, you are saying domain is going from 0 to infinity, including 0, and range is negative to positive infinity. All right, let's take a look at that. So domain, of course, we're talking in terms of the x-axis. So yeah, you can see on the original function, we start at the point 0, 0, and the arm of our graph is going to the right. So of course, that tells us this arm is going towards positive infinity. So for domain, yes, you are starting at 0, including 0, and going to positive infinity. Now, as far as range goes, Meredith, if you think about this, we have no graph on the negative y-axis, right? Which means you wouldn't be starting at negative infinity. Even in terms of the y-axis, where is our graph starting at? Yeah, very good. You are actually going from 0 to infinity because again, we are at the origin 0, 0. And even though our arm of the graph is going to the right, we know it's going to get wider, which means it's going to start going upwards. So even in terms of the y-axis, we're starting at 0 and we're going up. So that's going to be from 0 to positive infinity. So the range is also the same as the domain in this case. Okay, so how does this get affected when we move the graph 9 units to the left now? What happens to your domain and range for the square root of x plus 9 function?
Does the 0 become -9?
Very nice, Julian. Yeah, so in the domain, since our function is moving 9 units to the left, so now you can see my second function is actually starting at -9 on the x-axis, and again, it's going to the right, which means it's still going towards positive infinity. So your domain will now start at -9, going towards infinity. Very good. And what about the range? Meredith, very good. Has your range changed?
Yes.
Okay, what do you think, Julian, is the new range then? In terms of the y values, where are we still starting at?
I guess it
Uh,
hasn't
0 to
changed.
infinity? Because, you know, our graph moved 9 units to the left, but did the graph move up or down?
No.
No, it did not, right? So actually in this case, what happens, guys, is the graph only moved 9 units to the left, so it definitely changed our domain. But you know, the two graphs are still on the same line. They're both still on the x-axis, which means we're still going from 0 to positive infinity. So in this case, your range did not change. You're still going from 0 to infinity because our graph did not move up or down. It just moved to the left. So it does not end up changing your range in this example. Julian, does that make sense?
Yes, it does.
Okay, very good, very good. All righty. Okay, very good, guys. So we have looked at vertical movement or vertical translation. We have looked at horizontal translation. And remember, these were all part of those rigid transformations, which means the shape of our graph did not change. It just got moved around, you know, up or down, right and left. Now, another rigid transformation we have is reflections. Of course, as the name suggests, you know, we are talking about a mirror image of your graph, but basically, you're imagining that the mirror has been placed at the x-axis. So if the graph is on the upper half with reflection, of course, it gets reflected on the lower half and vice versa, depending on where your original base function was at. So they are saying basically to find the mirror image of a point, we simply change the sign of the y coordinate. And that basically comes from having this little negative applied in front of your function. So if your original function is y equals f of x and you just put a negative in front of the function, that's what basically creates a reflection. And I've just got a simple example over here. So the first function is y equals x, and then we're simply putting a negative sign in front of it, and that will give you y equals negative x. So if it's y equals x, again, I can use my basic 5 points over here. And since this is, remember again, the identity function, so y equals x, so whatever is the x value is going to become your y value. So these guys would basically be the same. Okay? And since we're only doing a reflection, we're not really moving it anywhere. I'm going to keep my same x values. We don't have to add or subtract anything to the x values. And in this case, what's going to happen now, because this function is negative of x, that means in front of every x value, you put a negative sign. So that changes this to a positive 2. Negative of negative 1 will, of course, become positive 1. Negative of 0, because 0 does not take a sign, will stay as 0. Negative of 1, so this guy, of course, becomes negative 1. Negative of 2 will become negative 2. So this is basically what they're saying. Change the y coordinate signs from the original function. So original functions where you had negative 2 and negative 1, they now become positive 2 and positive 1 in the reflection. 0, of course, will stay the same. And then the positive 1 and positive 2 now become negative 1 and negative 2 in the reflection function. So when you graph this, the original function, we've got 0, 0, 1, 1, 2, 2, then negative 1, negative 1, negative 2, negative 2. So this is basically your identity function, which ends up looking like this. Okay, so this is our y equals x function. Now with the reflection, we still had 0, 0, but then for positive 1, we have negative 1. For positive 2, we have negative 2, and these are these 3 points at the bottom that I'm doing. And now we'll do the negative 1, positive 1, and negative 2, positive 2, which will be over here. And of course, you can see how this reflection happens. And this is going to be your y equals negative x. So, basically what's happening is this part of our graph is getting reflected down here. And this part of our original graph is being reflected up here. Let me just show you quickly with our Desmos calculator here, just with colors. So you've got your basic x function, and then its reflection was the negative x function over here. And you can see with the colors, it kind of becomes more obvious because now you can see the green is the original function and the purple is the reflection. So you can see how that right-hand side of the green gets reflected on the negative x axis, or towards the negative y-axis, sorry. And then the left-hand side of our graph is getting reflected on that positive y-axis side. And again, remember your mirror is basically being placed on the x-axis itself. So that's the one acting as your reflective surface. So really, reflections are pretty straightforward because like it says, you are just changing the sign of your y coordinate to create these reflections. Oops. There we go. Are you guys okay so far? Did you have any questions? Nope. Okay. So one more reflection example. Again, we're coming back to our square root of x function. So remember, for square root of x, we cannot have any negative on the inside of our radical. So we'll use the same values we did before. We can do 0, 1, 4, 9, and 16. And I'll actually use the same x values here as well for our reflection function. These numbers will come out to be 0, 1, 2, 3, and 4. So remember, for the reflection function, you just need to change the signs on your y values So this guy will now become -1, -2, -3, -4. And just to show you how the math works out, because you have that negative sign in the front, when you do square root of 4, square root of 4 is 2, but that negative sign carries forward. And that's basically what happens on all of these y values. So when we graph this, you're going to have 0, 0, 1 and 1, 4 and 2, 9 and 3. This is our original function, y equals square root of x. And then when we graph the reflection, you're still starting at 0, 0, but now you are going down to 1, -1, 4, -2, and 9, -3. So that one now becomes your reflection. And remember, together, if you take both of these arms together, this becomes your x equals y squared function. Remember the parabola that opens to its right that we had seen in section 2.2. So that's basically how your reflection works out to be. Now, I did want to talk about what happens when we look at these reflections and what it does to our domain and range. So let's go back to the previous example, and then we'll talk about the domain and range for our square root function also. So you had y equals x and y equals -x. So let's do the first function, y equals x, which is this line with a positive slope going up. What is going to be the domain and range for y equals x?
Would domain be 0 and infinity?
Okay, not quite. Okay, Lori, you are saying negative to positive infinity? Yeah, because if you look at this, you can see this is a line that's basically going, with a slope of 1, +1. So basically you can see it's going towards the left and it's going to the right, which means in terms of the x-axis, it's going to be using both negative and positive infinity values because it just keeps going. And also in terms of the y-axis, the line is also going up and down. So since this is a straight line with a positive slope, you're basically looking at negative to positive infinity for both domain and range. Because Julian, if it was going to be 0, that means the line would have to be starting at the origin 0, 0. It wouldn't have that bottom half, right?
Yes, that makes sense.
Okay, very good. So how did our domain and range change when we did the reflection? So for y equals -x, what happens to your domain and range?
Would they swap?
Sorry, would you say that again?
Would the sign just swap?
Would the sign just swap? Okay, not really. Because, we always have to write, when you're writing these interval notations, we always have to put the smaller number first. So the negative infinity would still have to be written first. Yeah, Kendall, very good. So even though we did create a reflection in this example, you can see on the negative x graph over here, our graph is still going in both directions, right? So in terms of the x-axis, we still have that arm heading towards the right-hand side and the left arm, of course, going towards negative infinity. And again, if you look at it in terms of the y-axis, we still have the arm going up and the other arm going down. So even though we have a reflection, but again, guys, these are straight lines. So since these are straight lines, it really did not affect our domain and range when we did the reflection. So you're still going from negative to positive infinity on both domain and range. So in this example, it does not change when we create a reflection. But what happens in this example here where we did square root of x and negative square root of x? So let's do the original function. And then let's do the reflection. So for square root of x, what's your domain and range? And we just talked about this example, what was it, in number 4?
So now it would be 0 and infinity.
Yeah, very good. It will be 0 to infinity. Oops. Yeah, including 0, you're going to infinity. And of course, as you saw in example 4, that is also the same thing for the range because you're only on the upper half of the y-axis and the right half of the x-axis. Okay, so that was the original function. Now, how does your domain and range change for the reflection? Or does it change, I guess?
Negative now, infinity.
Okay, so in what sense? Let's talk about the domain, the x values first. So you can still see our function, the reflection, the bottom half, it's still at the origin and it's still headed to the right. So even though we created a reflection, did it really change the domain of the function?
No.
No, it did not. Yeah, very good, because we're still starting at 0, 0, and our graph is still headed to the right-hand side. So as far as the domain goes, it has not changed. You are still headed towards positive infinity over here. But what happens with the range now? Because now your graph was on the upper half. When we did the reflection, it is now on the lower half. So how does that change the range? Or does the range also stay the same?
Is it negative now?
Okay, so how would you write it, Julian?
0, negative infinity.
Okay, so as I was telling you before, we always want to put the smaller number first. So in this case, since negative infinity would be smaller than 0, you're actually going to write this as negative infinity to 0, and then of course you're including 0. So you do have to actually switch your sides. Because you know, this arm of our reflection part of the graph is going downwards now, right? So it's starting at 0, but now it's headed downwards, which means it is going down towards negative infinity. And just with the way you write interval notation, we have to put negative infinity first and 0 as our second number.
That makes sense.
Does that make sense, guys? Okay. And you know, as I was telling you before, domain and range will show up pretty much in each chapter, each section. So just practice with this as much as you can until you get comfortable. Okay. All right, so we've looked at all the 3 different types of rigid transformations where the shape of your graph does not change. Now, what they're talking about here in this little paragraph is basically they're saying that, you know, if you are taking the y equals x squared function, which is your parabola, and you're reflecting it in the x-axis, and then moving it 1 unit upwards, they're basically saying the equation for this new function after the transformations will come out to be y equals negative x squared plus 1, because you know they're telling us first we do the reflection and then we do the translation by moving it 1 unit up. Now they are saying if you did the translation first, if you move the graph 1 unit upwards and then you did the reflection, you are actually going to get a different equation because you are moving the graph first 1 unit up, so that's where you add 1, and then you take the reflection on the entire function. So you actually end up getting negative x squared minus 1 as your function. So you can see, of course, depending on which transformation we did first, is going to make a difference on what kind of equation you get. In the first one, we did the reflection first and then translated 1 unit up. In the second example, we translated it 1 unit upward and then did the reflection. So what happens is the order of your transformation, how you do it is very important. Because as you can see, if somebody did it one way and somebody did it the other way, you're going to get two different equations, but that also means you're going to get two different graphs. So let's take a look at what each of these graphs would look like. So we'll go ahead and graph our x squared function first to get our base function. And then we'll do the first one, which was the negative x squared plus 1. Oops. So that's this guy over here. And you can see they talked about, and let me show you this in steps. So we first did the reflection as they told us, and then we did the translation. So when you add that 1, you can see instead of starting at 0, 0, that graph now moves 1 unit upwards. Now for the second graph that you had here, which was you translated 1 unit up first and then do the reflection, which is our negative x squared minus 1. So that guy will end up looking like this. So let me get rid of this guy here. So the black graph is our original function, the y equals x squared. You can see if we do the reflection first and then move it 1 unit upwards, you get the graph in red. But if you move it 1 unit up and then do the reflection, you get the graph in blue. So you can see those red and blue graphs are not the same graph. So the order of translation really makes a big difference in this case. So that's why you will notice when we finish talking about our little stretching and shrinking example here, they actually give us an order in which we need to do these translations so that we make sure everybody is going to get the same graphs. It's kind of like, doing order of operations with please excuse my dear and Sally, kind of that same concept here with the order of operations. Okay, so remember with stretching and shrinking, it actually changes the shape of your graph. So these are what we call as the non-rigid transformations. So here they're talking about to get a stretch, the number that we multiply our y coordinate by has to be a number larger than 1, and that will give us a stretch. For a shrink, if we multiply our y coordinate by a number which is between 0 and 1, that will shrink our graph. So basically what they are talking about is this a value right here in the front of your function. If you're multiplying your y coordinate by an a which is greater than 1, we will notice stretching in our graph. If you multiply by a number which is between 0 and 1, we're going to see shrinking happening in our graph. So we're actually going to do both stretching and shrinking in this example over here. So we've got our base function, which is y equals x squared. Our next function is y equals 1/4 x squared. And the last one is y equals 4 times x squared. So as you can see, the 1/4 is the number between 0 and 1. So we should expect to see shrinking happening in that function. 4, of course, is a number greater than 1. So this is where we should notice the stretching happening on our function. So let's go ahead and take a look at this. So we've got our, again, 5 basic points, -2, -1, 0, 1, and 2. So these guys will give us 4, 1, 0, 1, and 4. So that's going to be this guy over here. Okay, so this is our base graph, y equals x squared. Okay. Now, when we talk about, shrinking our graph by 1/4, if you actually keep the same x values, but what's going to happen to all your y values now, since you will be multiplying it by 1/4, you're actually going to end up getting, like for this first one over here, you will have 4 multiplied by 1/4, which will of course end up giving you 1 as the answer. So that will happen for both +2 and -2. You will end up getting 1 as the answer here. For -1, these points over here where you're getting +1 as your y value for -1, +1, you will be doing 1/4 times 1, which will of course give you 1/4. So these points will now be 1/4, and anything multiplied by 0 is going to be 0. So these numbers will just, shrink basically by 1/4. So now when you try to graph these, at +2, we are at 1. At -2, we are at 1. We're still at 0, 0, but now for +1 and -1, you just add a quarter over here. And so when you try to graph this guy, it's actually going to end up looking something like this. So what happens in this case, your shrinking is actually making the parabola, which was your original shape, become a little bit more wider of a parabola. So the shrink is happening in terms of where it's losing its shape, and instead of staying at that good parabola shape, it's actually now making it into a wider parabola. So let me show you that on our Desmos over here. So we've got our basic x squared function. Now we are doing 1/4 on x squared. So you can see here, again, the black is the original function, and you can see with that 1/4, our parabola has lost a little bit of a chip and become a more wider of a parabola. So that's kind of what happens with the shrinking. Now let's see what happens when we do stretching, when we multiply by that +4. So keeping the same x values, but this time all our original y values will get multiplied by 4. So you will have 4 times 4, which will give you 16. So that will be for +2, -2. When I multiply 4 with 1, of course 4 times 1 is 4. So that will be for -1 and +1. 4 times 0, of course, is still going to be 0. So now what's happening, we're still at this origin 0, 0, but at +1 and -1, we are at 4, and then +2, -2 is 16, so I won't be able to graph those. But now you can see how that stretching is happening, right? So it's actually making our graph narrower. So if it helps, you can think in this terms of the shrinking is making our graph wider, and the stretch is making our graph narrower. So let me show you here again on Desmos. Okay, so the purple is our stretching graph. So again, black was the original, green is the shrinking, and the purple is the stretching. So kind of think like of a rubber band, what happens when you stretch it, it makes it narrower. So that's kind of the effect that's happening here with this parabola. Any questions on this, guys? Okay, what do you think is going to happen to the domain and range for all 3 of these functions? So just looking at the graph, by doing that stretching and shrinking, did it change the domain and range? Okay, Morgan, you are saying domains will all be the same? Yeah, looks like it, because even though the stretching and shrinking is happening, uh, the arms of our parabola are still going to be heading in the right and left direction, which means they're all going to be staying the same. Okay, Evelyn, you're saying same. Morgan, same thing for the ranges. Okay, yeah, Meredith, very good. So yeah, good job, guys. So in this case, even though all of these shape changes happen, of course, for this particular example, your domain and range did not get affected. So for all 3 of these functions, our domain and range are going to stay the same. Domain is going from -infinity to +infinity, so it's using all the x values. As far as your range goes, all of them have the lowest point at the origin, which means we're starting at 0 and going upwards to +infinity. So as you can see, the stretch and shrink did not really make a difference on our domain and range here. Alrighty, guys. So here they're basically talking about how you can just take your y values and shrink them by, multiplying them by 1/4. Same thing with the y values for the 4x square function. You can basically stretch it by multiplying by 4, kind of like what I showed you. Now, this one here is what I was talking about, where you have multiple transformations, how you need to put them in order. So as you can see, this is our base function over here, where you've got horizontal translation, vertical translation, reflection, stretching, and shrinking. So the H value, the horizontal translation, is the first movement we do. So we always move our graph horizontally first. Then reflection, stretching, and shrinking can all happen at the same level. Now remember, you can have reflection and either stretching or shrinking. Obviously, in the same function, you cannot have both the stretching and the shrinking happening. So basically, you can do your reflection and then one of these as your next step. So horizontal translation, then reflection, stretching, or shrinking. And the very last movement we do, the very last translation we do, is going to be your vertical translation. So that is always going to be the last one. So horizontal first, vertical last, and then basically your reflection and stretching, shrinking in the middle. So this example here that I have is just to kind of show how the transformation happens. So the first thing we actually have to do is think about what our base function is. So if we removed all these numbers that you were adding or subtracting or multiplying, what would our base function be here in number 8? So what do you think is the original function that we are transforming here? Meredith, it is not y equals x. Oh, you guys are so close. It's not x squared either. Yeah, it is actually square root of x, because like I was telling you, just imagine if you did not have the -1/2 in the front, you didn't have the +2 and that +4, what would you be left with? Which is the square root of x. So that's actually our base function over here. So this first table we are going to create for that base function of square root of x. Okay, then you have to go in order of these multiple transformations here. So as they're telling us, we have to do the horizontal translation first, which is your h variable. And of course, remember the h variable is where it's being added or subtracted to the x variable itself. So that actually means it's coming from here, right inside our radical, where you have square root of x plus 2. So your second table is actually going to be for that horizontal translation. So this will be just for the value of square root of x plus 2. Then, of course, we know reflection and then stretching or shrinking happen at the same stage. So you can see we have that little negative sign in front of the 1/2. So the negative is telling us we do have a reflection. So that will be your next table, I guess. So we'll just use that negative in front of the square root of x plus 2. Now, since these guys are at the same stage, you can also just do 1/2 over here, and then you can do the reflection in the next one. So those guys are kind of interchangeable because they are at the same level. So it doesn't matter. I'm just doing the reflection first, but if you want, you can do the shrinking, which that 1/2 tells us our graph will be shrinking. So we will be doing then -1/2 square root of x plus 2. So that's taking care of the reflection and the shrinking. And then of course, the very last one is where we do the vertical translation, and your vertical translation is coming from that positive 4 at the end. So that would basically be the whole function now. So negative 1/2 square root of x plus 2, and then the plus 4 at the end. So you know what happens is if we can take this in stages, then you can kind of see how each one of these values will change as these transformations happen. So, you know, of course, our original base function is still square root of x. So with square root of x, we cannot have negatives in there, which means we again start with a 0, and we go 1, 4, 9, and 16. So we know those values will come out to be 0, 1, 2, 3, and 4. So if we try to graph this as our base function, then of course this is our square root of x function. So this is our base function that we're trying to transform. Okay. So now with the horizontal translation, what do you think is going to happen to our x values with the square root of x plus 2 for our second table? Where is our graph moving when you do that square root of x plus 2? Because it's horizontal translation, so are we moving to the right or left? So what did we talk about with the translation for the horizontal translation? What happened? Julian, you're saying right? Okay, remember what I told you with the horizontal translation, you have to go with the opposite sign. So since it's x plus 2, remember technically that means you have x minus negative 2. So that actually means your graph is being moved to the left, not the right. The vertical translation is really the only one where positive means up, negative means down. But with horizontal translation, you have to go in the opposite direction. So when they tell you it's x plus 2, that means 2 itself is a negative number and your graph needs to be moved 2 units to the left. So this guy is actually moving to the left, which means from each of our x values, I'm going to subtract 2. So each of our x values, the original that we had used, subtract 2 from each of these, which will end up giving us negative 2, negative 1, positive 2, positive 7, and what would that be, 14? And you know, of course, once we put this inside the radical, you'd be adding 2 again. So you will essentially end up with the same numbers again. So you should have square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. So the same y values as the original. So the only thing that's happening is, remember, your graph is moving 2 units to the left, but your y values are still staying the same. So you should still have the same exact curve. The only thing is you've now moved it 2 units to the left. So let's see what this graph ends up looking like. So now you're at negative 2, 0, negative 1, 1, positive 2, positive 2, and then what else did we have? 7 and 3. So now, oh, this was the wrong place. Here we go. So this is basically the original graph that has now moved 2 units to the left. Okay, and let me show you the little transformation that happens here. So we're doing square root of x square root of x plus 2. You can see the black is the original graph and the red is just that graph being moved 2 units to the left. Okay, then we were doing reflection after that. Okay, so reflection basically means we'll keep the same x values from the previous table, but now since we are doing this reflection, that means we're just putting a negative sign in front of all of our y values. So now you will have -1, -2, -3, -4, right? We're just creating the reflection from step 2. So in this case, that means we're taking this second graph and reflecting it. So now you will be starting at 0, 0, but now you're at -1, -1, +2, -2, and then let me see, 3, 4, 5, 6, 7 at -3. So just using all of those ordered pairs to come up with our graph. And this is our reflection. So this is y equals negative square root of x plus 2. Okay, so again, just to show you here, this is negative square root of x plus 2. So you can see that's our reflection over here. Now this is where the shrinking is going to happen, because now we have to multiply by that 1/2 in front of our square root of x plus 2. So again, we're keeping the same x values here. We're not changing them. So keeping it at -2, -1, 2, 7, and 14. But now your y values are going to change, because each of these y values that you have here in table 3, you need to multiply them with that 1/2 to make that shrinking happen. So of course, if you did 1/2 times 0, you get 0. 1/2 times -1 will of course give you -1/2. 1/2 times -2 will give you -1. That should be -1. Okay. 1/2 times -3 will of course give us -3/2, or basically 1.5. And then 1/2 times -4 will of course end up giving you -2. So we've got a couple good points that we can use in here, and the 1/2 and the 1.5, or the -3/2, we can kind of guess where those points will be, so they can kind of help us be guidelines. But now we are at -2, 0, so we still have the same starting point as our reflection graph, but now we're shrinking all of these basically by half. So you should be at 2, -1, which is a good point right over here. We've got, well, we won't be able to use 14, but we've got 7 at -1.5. So 7 will be here at -1.5, which means you're right here halfway between our graph, right? And all of these points have shrunk basically. So this guy should be at half over here. And then if you draw your graph through that, it's basically just going to make it get closer to the x-axis, because that width that you are seeing between the x-axis and our reflection graph is going to shorten basically by half, because that's how that shrinking is happening. So that gives you your shrinking right over here, -1/2 square root of x plus 2. So again, guys, just to show you on our Desmos calculator over here, and let me put a 1/2 in the front. Okay, so you should be able to see that graph in green, how the graph in blue has basically now shrunk, and that distance has basically shortened by a half. And so that's kind of what happens with the shrinking in this case. So now we have done our horizontal movement. So we moved our graph 2 units to the left, then we did the reflection, and now we've taken care of the shrinking. So the only thing left to do at this point is that final step, which was the vertical translation by adding that 4 at the end of our function. So again, what's going to happen in this case is we are going to keep the same x values, because again, we're not moving our graph horizontally anymore. So keeping the same x values, but now to each of the y values that we have in our table 4, you are going to add 4 to all of them to get the y values for this very last table. So you've got your 0 plus 4. So of course that will give you 4 for the first value over here. We've got negative 1/2. So when you add negative 1/2 to 4, what do you get? And what would the rest of that table be once we add the 4 to it? Yeah, 3.5. Or basically, if you want to leave it as a fraction, that would be 7/2. For the next one, when we add negative 1 and 4, yeah, you're going to get 3. What happens with negative 3/2 when you add 4 to it? Or basically negative 1.5. Yeah, negative 3/2 plus 4 will give you 2.5, or basically as a fraction, you can write that as 5/2. And even though we won't be able to graph it, when you take negative 2 plus 4, what will we get?
2.
Yeah, 2. So, unless you expand your graph, we won't be able to graph it, but it still gives us an idea of where we're headed. So we've got negative 2, 4. So basically what's happening is this fourth graph that we drew is now being moved up 4 units. So all of these points are moving up by 4 units. So negative 2 from 0 is now going to 1, 2, 3, 4. So he's coming up here. Then we had, let's see, negative 1 at 3.5. So that would be 1, 2, 3, 3.5 would be here. Then let's see, what did we have? 2 and positive 3, so positive 2, positive 3, and 7 at 2.5. 7 at 2.5. This one is going to end up looking like this. So this guy here is our final. And just to show you this on Desmos again, you're just taking this last part and you're literally just adding 4 at the end of it. And you can see this graph, which was originally in green, has now moved 4 units up. So if we, let me see if I actually just get rid of these other ones here. Okay, so you can see the green has been moved 4 units up, and of course the black was our original graph. So by the time everything is said and done, your original function of square root of x, of course, moved 2 units to the left, then it got reflected, and that's why you're seeing your curve is now upside down. It got shrunk by 1/2, so it's not quite as wide as the graph in black, and then of course it got moved 4 units up. So that's a big transformation that happened from what we had as the original function, and by the time everything is said and done, you have a completely different graph over here. So that's kind of how these multiple transformations have to be taken care of. Start with the horizontal translation, then your reflection, stretch or shrink can happen at the same level. And then the very last translation we do, of course, is the vertical translation. So just for the final graph itself, not the intermediate ones, what do you think the domain and range will be? Now remember, for the original function that we started out with, your domain and range, and again, we've looked at this graph multiple times, was 0 to infinity, including 0 for both domain and range. For the final function, which was y equals -1/2 square root of x plus 2 plus 4, what do you think the domain and range will be? So I don't know if this graph is more helpful or if this guy would be more helpful.
Would the domain be -2 including, okay, so including -2 to positive infinity?
Very nice. Yeah, very good. Because as you can see in this graph here, we are in line with -2 over here. Let me see. Let me see. You can see the leftmost point is right here in line with -2. And of course, our graph is headed to the right. So you are going towards positive infinity. So we are looking at, oops, not you, a domain of going from -2 to positive infinity. Very good, Morgan. And then what can we say about the range? Because I don't know if zooming out will kind of help you see.
Negative infinity including 4. Yeah.
Yeah, very good, Morgan. And Mackenzie also sent us negative infinity before. Yeah, very good. And again, let me go back. So you can see here again that we have on the y-axis, our graph is in line with +4 over here. But as you can see, this graph is definitely headed downwards, right? It is going to keep going down, which means it is going towards negative infinity. So yeah, very good. Good job, guys. You are starting at, well, technically you're going from 4 to negative infinity, but basically the way you write this, you are going from negative infinity to 4, including 4, because the idea is you're coming down and you're stopping right there at +4. So in this case, you can see by the time we got all the transformations done, your domain also changed and range also changed. And it's no surprise if you notice here that our domain goes back to -2, which is how many units our graph moved to the left. So that's reflected in the domain. We know we moved our graph 4 units up, and that's reflected in your range. And also because of that reflection, we are now going from negative infinity to 4. If there had been no reflection, our graph would still be going towards positive infinity, but it's that reflection which ended up moving our graph towards negative infinity instead of positive infinity. So, each function is going to be so different based on, are you looking at a parabola? Are you looking at a square root function? Are you looking at a straight line? All of those can have a difference on your domain and range, and of course, what the final result will look like. So before we move forward, did any of you have any questions on this? No? Okay. So this one is getting into the linear family of functions. So what happens with linear family of functions, you can still kind of have that same concept of, reflection, stretching, shrinking, and then your graph being moved up and down or left or right. So what happens in this case, your basic function for a linear family of function is always the identity function, which is your f of x equals x, or basically your y equals x function over here. So that's always the base function for the linear family of functions. And then any kind of transformation you do is basically going to change basically the slope of your line and where your y-intercept is going to be. So essentially what happens is you can take this transformation form, which is a times parentheses x minus h plus k, and you can rewrite it as your slope intercept form, y equals mx plus b. So you can see here they're starting out by distributing that number a into the parentheses, so you end up getting a times x multiplied and then negative a times h. Now, of course, a times x, x being your variable, you can think of that a being the slope of your line, and you can rewrite that part as mx. And then this negative ah plus k, this is actually all numbers because a is a number, h is a number, k is a number. So you can go ahead and combine all of them, simplify that, and that can become your b value, which is your y-intercept. So all transformations for linear family of functions will actually end up looking like your f of x equals mx plus b, where m would be the slope of your line and b would be the y-intercept, right? And so in that case, when you're talking about this linear family of functions, you've got, as you can see in example 9, y equals negative 2x plus 5. Now, if we talk in terms of transformations, that negative is, of course, reflection, right? That 2 is telling us our graph is going to stretch, and that plus 5 is telling us our graph is moving up by 5 units. But now if you graph this, just you would normally graph a line, hopefully we will be able to see that transformation happen. So what I'm actually going to do is graph our base function y equals x first, which will be at 0, 0 as the origin. And it's got a slope of 1, right? So that means you're just going up 1 unit and right 1 unit, or left 1 unit and down 1 unit. So this would be our basic y equals x line. Now when we try to graph this function y equals negative 2x plus 5, that's telling us the y-intercept is at positive 5. So right here, and then you've got a slope of negative 2, which means you go down 2, right 1, go down 2, right 1. Or you can go up 2, left 1, up 2, and left 1. And you can see this is kind of what this line will end up looking like. Oops. I know, somewhere in this direction. And this is your negative 2x plus 5. So you should notice, just by comparing where the line crosses the y-axis at, you can see you're at 0, 0. And let me see if this will let me do this. So you're at 0, 0 on the original function, but this has now moved 1, 2, 3, 4, 5 units up. So you can see that's that vertical movement that happened with 5. Now, of course, the reflection is evident because you're now at a negative slope instead of having that positive slope like y equals x does. The other thing you should notice is the steepness of the line. And that's where that stretching of multiplying by 2 is happening, because the slope of the line is pretty steep on that reflected line. And that's because of that multiplying by 2. But that's basically what happens when you're looking at transformation on linear functions or straight lines. Your y-intercept will change if it is crossing the y-axis, and then the steepness of your line can change, and then based on if you have a positive or a negative slope, the direction of your line can change. But that's what transformations will end up looking like for these linear family of functions. Does that kind of make sense, guys? How the linear transformations work? Okay. Alrighty, let's take a look at symmetry here. Now your functions, when we are talking about symmetry, of course we have symmetry in terms of reflection also, because if you're just reflecting the graph on the x-axis like we did with all of these examples over here, if you fold your graph along the x-axis, basically the two graphs will coincide. Or if you think about in terms of distance, if you take the distance from this point on the x-axis, this distance here is going to be the same as this distance here. And of course, same thing on the left-hand side, this distance is the same as this distance over here. But normally, when we talk about symmetry, we're not really looking at reflection in the x-axis. We're interested more in terms of the y-axis and the origin. So if you take a look at just the f of x equals x squared function here, if I fold this graph right along the y-axis, right, the vertical axis, then the distance from these points on the y-axis, this distance here is going to be the same as the distance on the left. This distance here is going to be same as the distance of the left. If you just fold your graph along the y-axis, the two halves will also coincide. And all parabolas have this symmetry. It doesn't matter if the parabola is opening up or down, or if the parabola is opening right or left. If they're opening up and down, they will have symmetry in terms of that vertical axis. So it can be the y-axis or whatever other axis of symmetry they might have. If your parabolas are opening right and left, then it will have a horizontal axis of symmetry. So it could be the x-axis or it could be any other points. But like I said, normally when we're talking about symmetry, we're talking about symmetry with respect to the y-axis or with respect to the origin. So when we're talking about symmetry with respect to the origin, you can think of this graph over here, f of x equals x to the third, or the cube function. So in this case, you can't really do the folding thing because, origin is just a point, it's not a line. So we actually use the idea of distances. So if you look at this origin over here and you take the distance to those 2 points, the distance from 0, 0 to the point 2, 8, this distance is going to be the same from origin 0, 0 to the -2, -8. So these distances are actually going to be equal. So functions that are symmetric about the origin, you can always take the distance from the origin to 2 points on your graph and you can see if that distance is going to be equal. But when functions are symmetric about the y-axis, then yeah, literally you can fold your graph in half along that line and you will see the two graphs will coincide, because again, those distances from the line of axis, or what we call as axis of symmetry, will definitely be the same. So functions like the x squared function are what we call as even functions, and all even functions are going to have symmetry with respect to the y-axis. And the easiest way to find out if you have an odd or even function is you take your original function and replace it with a negative x instead of the positive x. And if you come back to the original function, you have an even function. So what that means is if I take my original function of f of x equals x squared and replace my x with a negative x. So if I'm putting negative x into this function, we will do negative x to the second power, which is negative x times negative x. So the two negatives will become positive and you'll end up getting positive x squared. So you can see we still end up getting the same function that you started out with. So this only happens if you have an even function. And all even functions, like I said, are going to have symmetry with respect to the y-axis. Now, when you're looking at functions like x to the third power that have symmetry with respect to the origin, in this case, what happens is when you plug in the negative x in your function, it actually ends up making your entire function negative. So what that means is if I take my f of x, which is x to the third power, and replace my x with a negative x, now I'm going to put negative x to the third power. So that's, of course, negative x times negative x times negative x, 3 times, right? So the two negatives will become positive, but then you'll still have a negative sign left behind. So you will end up getting negative x to the third. So as you can see, it ends up making a negative out of the original function. So if you get a negative on the original function, that means you have an odd function, and odd functions will always have symmetry about the origin. So that's kind of the way you test to see if you have an odd function or an even function. And you know, the easiest way I can tell you to remember this combination is odd function also begins with an O, and origin also begins with an O. So if you can remember that odd goes with origin, then automatically it will help you remember that an even function has to go with the y-axis. So odd is symmetric about the origin, even is symmetric about the y-axis. Okay? And this little part here is just talking about, if you can remember, anytime your exponent is going to be an odd number, you will always have a negative sign left behind. So if you did, like we did here, negative x to the third power, that 3 is an odd number, so we had a negative sign left behind. So anytime you do these calculations, if n is odd, you will have a negative sign left behind. If n is even, then you end up getting a positive result. So you just get a positive x to the n. So that can kind of help you through these examples over here, if you can remember this little, what happens when you raise a negative number to an odd or even exponent. So as you can see here, they're asking us to basically just use this idea and determine algebraically if we have an odd function, an even function, or if it's neither one of them, and what kind of symmetry does our function have. So what you have to do is take this function and replace your x with a negative x. So I might not have enough space here, so I'll show it to you over here. So we've got our original function as f of x equals x to the fourth power minus x to the third power. So replace your x with negative x, which means we will now have negative x to the fourth power minus negative x to the third power. So you're basically taking all of these x values and replacing it with negative x. And this is where this little thing will come in handy. So if you have n as an even number, you end up with a positive result. If n is an odd number, you end up with a negative result. So here you can of course see I have negative x raised to the fourth power. 4 is a even number. So this guy will end up becoming positive x to the fourth, keeping my minus sign in the middle. Then you've got negative x to the third power. And as you just saw, with that third power, that's an odd number, we will actually have a negative x still left behind. Oh, okay. Clinton, thank you so much for letting me know about that. I hope they'll let us make it through the end of class before they cut your internet off. Okay, sorry, I missed my exponent over here. So you will actually end up getting a negative sign left behind from that negative x to the third power. So the two negatives, of course, will end up becoming positive, and this will actually end up becoming x to the fourth plus x to the third power. And so what's happening over here is this guy definitely does not match this guy. We did not get the same result, because if we had gotten the same result, then we could have said this is an even function, but obviously we did not come back to the original function itself. And since that did not happen, this is definitely not an even function. So if it's not an even function, there is no symmetry with the y-axis. Okay, so we've made the decision it's not an even function, but then is it an odd function? Do we have symmetry with respect to the origin? So remember, for it to be an odd function, you basically have to have a negative on the original function. So if you're going to have a negative on the original function, basically what happens if I put a negative sign in front of my original function? So if I put a negative sign in front of my original function, So we'll need to distribute this negative sign inside the parentheses and see what happens. So we will end up getting negative x to the fourth. Negative times negative makes it positive x to the third. And again, we did not get the same result as we have here when we put that negative x in. So we're not even getting a negative of the original function, because then I should have had a negative x to the fourth and positive x to the third. So this guy is actually telling me it's not an odd function either. And that means no symmetry with respect to the origin either. So in this case, of course, our conclusion would be it's neither, and it has no symmetry. And you know, you can, just to verify that your result is correct, you can see what the graph of this looks like. But normally we do not try to depend on the graph for the simple reason graphs can be inaccurate, or they could not be showing you the entire picture. So if you do the x to the fourth to x to the third power over here, let me just show you what that original function looks like. So that's x to the fourth minus x to the third. And so first of all, you can see this is what you are noticing on this graph over here. But once you zoom in a little bit, look at that. You have no symmetry over here. Definitely not with respect to the y-axis, because you have a wider end on the right-hand side. And there's no symmetry with respect to the origin either, because you have to be on the opposite sides of the origin, and we don't have that either. So you can see our conclusion here was correct, that we do not have any symmetry. So this is neither, and it has no symmetry. Questions on this one, guys? Okay, so if we try to do that same thing by plugging in negative x in number 11, what kind of result do you think we'll end up with? If you replace the x with negative x, you basically get a negative of the original function, right? We definitely did not end up with the same result, because if we had gotten a positive x, then we would have known that the two functions are even, but obviously we don't have a positive x in our answer, so this is not an even function. So obviously no symmetry with the y-axis. So do we have an odd function then? Remember, to check for an odd function, you just end up putting a negative sign on in front of the original function. So if you put a negative sign in front of the original function, do we have the same result?
Yeah.
Yes, we do. Because you can see we ended up getting negative x for both results once we put that negative sign in. So this is actually telling us we actually have an odd function. Yeah, very good, Lori. We have an odd function, which means it is symmetric about the origin. And you know, of course, you know, we've done the y equals x function before. So if you can take a look at this graph over here, obviously you can see if we picked these 2 points, they are going to be the same distance from the origin. So if I pick this point here and I pick this point here, this distance is going to be the same as this distance over here. So they do have symmetry with respect to the origin. So that's kind of a neat way to also verify your answer. So this guy is an odd function. Okay, what do you think is going to happen on number 12 over here? This is an absolute value function that they are giving us. You have f of x equals absolute value of x squared minus 3. So of course we start by replacing our x with negative x. So that would mean you have negative x to the second power minus 3. And what will that end up giving us? What happens when you have negative x to the second power?
It just turns to x squared.
Yeah, it will turn into positive x squared. Yeah, very good, Lori. So you would basically, because, you know, of course, that's an even exponent. So negative x times negative x will become positive x squared, and then minus 3 over here. So obviously you can see we end up getting the same answer as the original function that we started out with. So in this case, we can say even when you plug in a negative x, it gives you the same result as the original function. So that tells us this is an even function. And even functions, of course, are symmetric about the y-axis. So again, just to quickly show you the graph for this guy. This is with absolute value. And then we've got x squared minus 3. You can kind of see, because of that x squared part, you have that little parabolic shape. And the minus 3 is, of course, giving you that y-intercept over here. But then it's still keeping that v kind of shape for the absolute value. And if you fold along the y-axis, of course, you can see the two halves will coincide. Or you can also think about this in terms of distances. So if you take the distance from you know, let's say from this point over here, and you take the distance over here, or you take the distance to the other side, this distance will be the same as this distance. So you know, again, it has that symmetry with the y-axis. So that's kind of what you are looking for when you are doing these examples over here. All right, so let me see what you guys come up with for number 13. What's your conclusion on that? What happens when you put negative x in? Is it an odd function, an even function? Okay, Lori, you're saying even? Okay, can anybody else verify that for me?
Yes.
Julian, okay. Anybody who got a different answer? Evelyn also says yes, okay. It is actually not an even function. Did anybody get a different result? Because you know what's going to happen here, guys, when we take that x and replace it with negative x, we're going to end up getting negative x plus 3, the whole quantity squared, right? So the other way for you to look at it would be if you went ahead and did a FOIL on the two functions. If you did x plus 3 times x plus 3, this first one, you would end up getting x squared plus 6x plus 9. So if we, replaced these x values with negative x, you would end up with negative x squared, negative x squared, then positive 6 times negative x plus 9. So when we clean this guy up, the negative x squared would definitely become positive x squared, but now we would end up getting negative 6x in the middle plus 9. So as you can see, we definitely do not come back to the original function because now your middle term will become negative. So it's not an even function. So no symmetry with the y-axis. But then the question is this an odd function? Okay, Evelyn, you're saying it's neither even nor odd. Okay, so just to verify to see do we have an odd function or not, take your original function and basically put a negative in front of it. If I did negative on my original function, that would be negative, and I'm using the factored, not the factored, sorry, the FOIL form over here. And if we put a negative in front of this, then we distribute that negative sign, we will end up getting negative x squared minus 6x minus 9. And again, this is not the same as this guy either, right? So this is not the same, which is like Evelyn said, we don't have an odd function either, which means no symmetry with the origin. So again, this guy would be neither. And technically, we will actually talk about this later on. This actually does have symmetry, so I kind of don't like saying no symmetry. I'll probably just leave it at neither for right now, because technically this function actually does have symmetry. And let me show you what that symmetry is going to be. So you will actually have x plus 3 squared. So you can see this function does not have symmetry with respect to the y-axis because we're not at the y-axis, right? This graph is 3 units to the left. It definitely has no symmetry with the origin, but it actually has symmetry with respect to this vertical line over here. And this vertical line actually happens to be the line x equals -3. So technically it does have symmetry. It's just not at the y-axis or the origin, because remember, this is a parabola and all parabolas have symmetry. So it's just a matter of, because they only want us to talk about in terms of the the y-axis or the origin, in terms of that, it does not have symmetry, but it has its own symmetry. So it's just a little bit different, but you know, in this context here, they just want to know if it's odd, even, or neither. So technically, it has no symmetry, or you can think of it as it has an axis of symmetry at the line x equals -3. It's just not at the origin or the y-axis. Are you guys okay with that? Yeah?
Yes, that makes sense.
Okay, very good. So just the last part here, guys, you can kind of see in this paragraph here, we're actually talking about how you can use the exponents on your x variables to also decide if you have an odd or even function or not. So if you just have a function like x squared, you can see that exponent is 2, which is an even number. So that actually automatically tells you you have an even function. Or you can have a function something like this over here, where you have x to the 6th power, which is an even number. In the second term, you have x to the 4th power, which is also an even number. X to the 2nd power, which is an even number. And this is kind of neat. They're thinking of that constant number 3. And they're saying you can think of that 3 as being x to the 0 power, 3 times x to the 0 power. We know with zero exponent rule, anything that has a 0 exponent will end up becoming 1. So you basically end up having 3 times 1, or the number 3. So you can think of the number 0 as being an even number, even though technically we don't really think of 0 as being even or odd. But you know, again, sometimes if it benefits us, we can think of 0 as being an even number. So that means this guy is also an even exponent. So if all the exponents in your function are going to be even exponents, you can think of all of them as being even functions. So you can use that same rule for odd exponents also. So if you have something like x to the 3rd power, that 3 is an odd number, which means this is an odd function. You can have a function something like this, where you have x to the 5th power, which again 5 is an odd number, x to the 3rd power, 3 is an odd number, or x to the 1st power, which again 1 is an odd number. Now you should have no constant term like that +3 here. Because that can only be an even function. So as long as all the x exponents have odd exponents, you can say these are all odd functions, which means, of course, their symmetry is going to be about the origin. For even functions, the symmetry is going to be about the y-axis. So that can also help you out. Now, if you have a combination of both odd and even, which this function has, I have x squared, which is an even exponent. I have x to the 1st power, which is an odd exponent. So since this is a combination of both odd and even, this will have neither of these two symmetries. So it will not be symmetric about the origin. It will not be symmetric about the y-axis. But again, guys, x squared plus 3x is a parabola, so it will bring its own symmetry. So we could have actually applied that idea here in the examples we did. So look at this number 13. When we multiply it out and you end up getting x squared plus 6x plus 9, you can see x squared has an even exponent, but then 6x has an odd exponent. So since this is a combination of odd and even, we had neither of those two symmetries. If you look at this function over here, you've got x squared, which is an even exponent. The number 3, again, you can think of that as being the x to the 0, which is again an even exponent. So this guy was an even function, symmetry about the y-axis. This example over here, you have x to the 1st power, which is an odd exponent. So this was an odd function with symmetry at the origin. The first one we did was a combination of odd and even exponents, x to the 4th and x to the 3rd. So as you can see, this guy was neither, and it had neither of those symmetries. So it really does kind of work in. So if you didn't want to, have to go through the calculations, which I think the calculations are not that bad and they give you a concrete answer, but you can also look at your exponents on the function to help you out. And then as I was telling you, we don't really include the x-axis symmetry, you know, because what happens with the x-axis symmetry, if we draw a vertical line through them, they're not functions, right? Because your vertical line would end up crossing them at 2 points. So normally we do not use the x-axis symmetry. So that would be examples like, you know, your parabola opening on the right. Now, a parabola opening on the right has symmetry with respect to the x-axis, but it's not a function. So normally we do not use the x-axis symmetry in these examples. Okay. And then the last part we wanted to talk about here is how actually you can use graphs to help you solve these inequalities. So basically the idea is if you can come up with a graph for these functions, then you can have, you can kind of see where the graph is crossing the x-axis at, crossing the y-axis at, and then kind of based on that, you can come up with what should be the solution set for these inequalities. And you know, otherwise we have the traditional method of solving these, which is what we saw in section 1.7. So here they're asking us to graph these functions and then come up with our interval notation for the solution set. So you can actually think of this here as being your function. So you can say y equals the quantity x minus 1 squared minus 9, and then graph this. You can use a table to graph this, or you can use transformations because your base function here is basically your x square function, because again, if you'd remove that minus 1 and minus 9, what you have is the x square function, which is being moved 1 unit to the right, because this x minus 1 is actually telling us our graph is moving 1 unit to the right, and this minus 9 is telling us we are moving 9 units down. So you can kind of use that also to help us out. So basically our graph, which would be at 0, 0, is now going to move 1 unit to the right, and it's going to move 9 units down. So it's actually going to be here. So instead of our lowest point being at 0, 0, it has moved 1 unit right and 9 units down. So that's one way of doing it, but you know, obviously we would need more points to help us out. So let's say if our original for the y equals x square function is -2, -1, 0, 1, and 2, which would give us 4, 1, 0, 1, and 4. If we transform this into our x minus 1 squared minus 9 function, all of your x values have to be moved 1 unit to the right, which means to all of your x values, you are going to add 1. And then since our graph is moving 9 units down, to all of your y values, you would be subtracting 9. So can you tell me what the new x value should be for our second table over here once you are done adding 1 to them? Yeah, very good, Lori. So yeah, -2 plus 1 will give you -1. -1 plus 1 will give you 0. 0 plus 1 is 1. 1 plus 1, of course, is 2. And 2 plus 1 will give you 3. Very nice. And then once you're done subtracting 9 from the y values, what are we going to get? Okay, so let me see. You should have 4 minus 9. Shouldn't that be -5 unless you're in the reverse order? Okay, 1 minus 9 will of course give us -8. 0 minus 9 would be -9. Okay, Lori, good. Again, same thing, 1 minus 9 will be negative 8, and 4 minus 9 would be back to negative 5. So negative 1, negative 5. 0 at negative 8, which is good because that's our y-axis there. 1, negative 9, and we already had done that just by looking at our translation. 2 at negative 8. So right here, and then 3 at negative 5. Okay, so your original parabola would have been here. Kind of this guy would have been original, and then after we move it 1 unit to the right, and 2 units, sorry, 9 units down, this is kind of what we're looking at. But you know what? I actually am interested in knowing where they are going to cross our x-axis at. We've already got the y-intercept over here, which was at 0, negative 8, but it would be kind of nice to know where these arms are going to be crossing the x-axis at. So let's go ahead and find our x-intercepts also, because they're going to play an important part in our solution set. So remember to find your x-intercepts. Basically, you need to set your y equal to 0. So in this equation that we have right over here, x minus 1 quantity squared minus 9 set equal to y, go ahead and set that equal to 0. So you can do x minus 1 squared minus 9, set that equal to 0, and we can find what our x-intercepts are going to be. So, start by moving your 9 to the other side, and then you would take obviously square root. So let me see what answers you guys come up with for your x-intercepts here. So move that 9. And then you would need to do square root. So what answers do you come up with? Now remember, when you do square roots, you should get one positive and one negative root. So be mindful of that as you're going through your calculations here. Okay, Julian, you came up with positive 4 and negative 2. Let me see if anybody else got that answer also. So if you did positive and negative, you should have, Evelyn also got negative 2, positive 4. Yeah, okay. So once you get rid of that square, you end up getting x minus 1 equals positive or negative 3, right? Square root of 9 would give you 3. And then add 1. And then, of course, that's where you come up with your two answers from. So positive 3 plus 1 will, of course, give you positive 4. And then negative 3 plus 1 ends up giving you negative 2. So that means we would be crossing our x-axis at negative 2 and positive 4. I'm actually going to need to erase my graph here. It should be going in this direction here, and then this guy would be crossing over here. Okay, and I'm going to remove my original function because we don't really need him. So once you have your graph, the way you have to come up with your solution set is basically looking at the inequality. So here where they're telling you that this inequality x minus 1 squared minus 9 is less than 0, they're basically asking you where are all the y values on this graph going to be 0 at. So of course, as you can see over here, you know, all of these values here below the y-axis are going to have y values which are less than 0, right? This is where the y values are going to be negative. Right at the x-intercepts, your y value is equal to 0. So right at the x-intercepts, y is equal to 0. And then above the x-axis is where y is positive. So they are interested in where is your inequality going to be less than 0 at. And of course, that happens right at that level below the x-axis. Which means when you're looking at the solution set for this, you have to use the interval notation that goes from this point right over here, which is our ordered pair -2, 0, and it's going to this ordered pair over here, which is 4, 0. So those are the two x values that we're actually interested in. So when they say your inequality is less than 0, your solution set for this inequality is going to be all the numbers that are between -2 and 4 with respect to the x values. So as long as your numbers are between -2 and 4, and actually they should be parentheses, not brackets, because we have a strictly less than inequality, there's no equal to. So that should be parentheses, because all of these x values that are between -2 and 4 will give you negative y values. If your value is -2 and 4 equal to, you get y equals 0. And if you use numbers outside of this range, you get y values that are positive. So since we know this is the area where our y values are going to be less than 0, that's going to stay between -2 and 4. Those are the only x values that we can actually use in our solution set. So that's actually how you use your graph in this case, is you have to see which part of your graph falls below the x-axis, and that is the area where your y is going to be negative or less than 0. So that's actually how the graphing comes into play. We will be looking at another method for solving these inequalities, which is going to be, I think in chapter 3, if I'm not mistaken, where they show us what we call as the test point method. But for this section, they are sticking with graphs. So you will see problems like this on your homework. Also, we have another example over here. We'll do a quick work on that tomorrow. So I was kind of hoping to finish 2.3 and start 2.4 today. Obviously, that didn't happen. So more than likely, I'm not sure if we'll get chapter 2 completed tomorrow either, because 2.5 is a little bit of a longer section. So I'll go ahead and put a deadline on your homework for the following Monday for chapter 2. So that should give you the weekend to finish any, okay? All right, guys, if you have any questions, let me know. And if not, I will see you tomorrow morning. Have a great day, guys. Be careful. Take care. Bye-bye.